Welcome to the deep dive. If you were listening to this right now, I actually already know something very specific about you.
You're a learner.
Exactly.
Yeah.
You are a learner. You have that, that insatiable curiosity, that drive to understand how things work.
You're always looking for that next big aha moment.
Right. But today's mission is a little different. We are not just talking about how to learn new facts or memorize trivia or hack your productivity.
No, we're going much deeper.
Yeah, we're looking at a multidimensional blueprint for how to literally, physically restructure and rewire your brain.
Which is incredible to think about.
It really is.
Yeah.
We are talking about sharpening your intellectual capacity, but doing it in a way where you don't just drown in information overload. We are pulling from an incredibly fascinating stack of research today, centered around the architecture of cognitive plasticity.
And the central premise here is, well, it's paradigm shifting.
It absolutely blew my mind.
Yeah.
The idea is that your brain is not a fixed vessel that just fills up with knowledge over time until it's full. It is a living, breathing, constantly rewiring entity. It's reshaping its own physical structure based on what you do every single day, and importantly, what you don't do.
That distinction really changes everything. I mean, when people hear a phrase like cognitive plasticity, they usually picture, playing random brain training games on their phone to get a higher score.
Guilty as charged.
We all do it. But what the research points to is a complete ecosystem of neuroscience, psychology, and education. It is about understanding the fundamental architecture of your mind and learning how to safeguard its adaptive potential for your entire life.
So it's not just a quick fix.
Exactly. It is a lifestyle architecture.
Okay, let's unpack this, because before we can even get to the high-level cognitive tasks, the source material makes it crystal clear that the brain needs a specific metabolic ecosystem just to function.
The biological bedrock.
Right. We have to start with exercise, nutrition, and sleep. And I want to start with exercise because, well, I always just assumed cardio was good for the heart.
Most people do.
But the research details this process called angiogenic remodeling. What exactly is going on in the brain when we go for a run?
Think of angiogenic remodeling as a major infrastructure project inside your head. When you engage in sustained aerobic activity, your body literally builds new blood vessels.
Wow.
Yeah, it expands the vascular highways in your prefrontal and parietal cortex to deliver more oxygen. And that physical expansion triggers a flood of a protein called BDNF.
Brain-derived neurotrophic factor.
You got it.
I have heard BDNF described almost like miracle grow for the brain. Is that actually accurate?
It is a great analogy, actually. BDNF kicks off neurogenesis, which is the actual creation of brand new neurons.
Just from running.
Just from aerobic exercise. And it does this specifically in the dorsolateral prefrontal cortex. To translate that, it is the area of your brain that acts as the main hub for abstract reasoning, planning, and executive control.
So you are physically building out the hardware required for higher level thinking.
Exactly. You are pouring the concrete for the foundation.
But I noticed the research gets incredibly specific about diet too, like down to the exact vitamins.
Yeah.
It seems like all that exercise might be completely useless if you aren't fueling the new infrastructure.
It is.
So why is the brain so remarkably picky about things like zinc and B vitamins?
What's fascinating here is how these three biological pillars function not as isolated prescriptions, but as an interdependent triad.
Okay.
That aerobic exercise we just talked about is incredibly powerful, but it is metabolically constrained. If you are running 5 miles a day, but your brain lacks dietary substrates like the B vitamins, folate, and zinc, you run into serious trouble with something called the kynurenine pathway.
The kynurenine pathway. That sounds ominous. What happens when that goes wrong?
Well, without those specific nutrients, the kynurenine pathway basically shifts gears. It starts producing neurotoxins instead of helpful compounds.
Oh, wow.
Yeah, and this leads directly to neuroinflammation. And this is where we have to look at the fats you consume, specifically the ratio of omega-3 to omega-6 fatty acids. Keeping that ratio balanced with plenty of omega-3s like DHA keeps your microglia happy.
Microglia, those are...
They're essentially your brain's microscopic cleanup crew. When the ratio is right, they stay in a resting, anti-inflammatory state known as the M2 state.
So if your diet is off, your microscopic cleanup crew gets inflamed and they just stop doing their job.
Precisely the opposite of what you want. Inflamed microglia stop performing synaptic pruning.
Which is?
It's the process where the brain cleans up inefficient neural connections. And if you cannot prune the dead weight, your brain's processing speed plummets.
Which brings us perfectly to the third pillar, because that cleanup process is deeply tied to sleep. The findings on slow-wave sleep really stood out to me. The research describes something called the glymphatic system kicking into overdrive. Can you explain how this works?
The glymphatic system is like a night shift street sweeper for your brain. During deep, slow-wave sleep, your brain cells literally shrink slightly.
They physically shrink.
Yes, and this allows cerebrospinal fluid to wash through the tissue, flushing out metabolic waste products. The most critical waste product it clears out is amyloid beta.
Right, that's a protein that builds up during waking hours.
Exactly. If amyloid beta isn't cleared out, it literally gunks up your synapses and impairs how your neurons communicate.
And while that physical washing is happening, the brain is also doing that synaptic downscaling you mentioned,
Right.
trimming away the redundant connections from the day so that the really important neural pathways have less background noise.
Then, as you move into REM sleep, your brain takes the novel information you learned that day and integrates it into your existing problem-solving frameworks. You are literally connecting the dots while dreaming.
The part that was a massive aha moment for me, and something anyone listening really needs to take to heart, is how fragile this all is. The study showed that even a single night of disrupted sleep throws off what they call cortical thinning dynamics.
Just one night.
Just one bad night of sleep impairs your inhibitory control, which immediately degrades your fluid reasoning the next day. You are quantifiably worse at solving new problems just because you stayed up late.
It is a delicate neurochemical ecosystem. If you compromise the sleep, the nutrition, or the vascular support from exercise, the foundation crumbles. But here is the catch.
There's a catch.
Having optimal metabolic health is still not enough. A biologically perfect brain that is never challenged will still atrophy. You have to intentionally disrupt your cognitive homeostasis.
Because comfort kills neuroplasticity.
Exactly.
Our brains are incredibly lazy, right? They love habits. They want to conserve energy by running on autopilot.
They do. But the research shows that to grow, the brain requires predictive coding errors. Basically, you have to surprise your brain and invalidate its existing models with unfamiliar, difficult stimuli. You need friction. We naturally shy away from making mistakes, but neurobiologically, a mistake is a signal. It tells the brain that its current neural model is inadequate and must be upgraded to survive.
A great example the source material gives for creating that friction is learning a highly complex multimodal language like Mandarin or Navajo, which is daunting. I struggled just to remember my high school Spanish, let alone a tonal language. Why do these specific languages force so much brain growth?
Those specific languages are incredibly demanding because they force cross-modal neuroplasticity. You are not just memorizing vocabulary flashcards, you are engaging in simultaneous auditory discrimination and something called tonotopic reprogramming.
Tonotopic reprogramming.
Essentially, you are having to tune your brain's auditory receiver to process entirely new pitches and tones that change the meaning of a word. You also have to navigate nonlinear grammatical parsing.
So it's a massive cognitive load.
Huge! This intense, multifaceted demand forces your brain's language center, the left parasylvian network, to radically rewire itself. It even recruits supplementary motor areas just to figure out how to physically control your intonation.
And the key is that you cannot just passively listen to a language tape. You have to generate intentional errors. Deliberately mispronouncing something, speaking it out loud, and getting real-time feedback is exactly what creates those predictive coding mismatches.
The embarrassment of getting it wrong is the active ingredient for neuroplasticity.
Here's where it gets really interesting. The research introduces this concept of constraint-induced problem solving. It gives this wild, highly specific, hypothetical, imagine trying to solve non-Euclidean geometry riddles, but you are forced to do it with one hand physically tied behind your back.
It sounds absurd at first.
I burst out laughing when I read that. But the underlying science makes total sense. Why would artificially limiting our physical or mental options help us learn?
It forces the prefrontal cortex to panic in a good way. When you restrict a familiar strategy, the brain has to repurpose entirely underutilized cortical territories to solve the problem. It is cognitive cross-training. When you impose severe constraints, you induce dendritic arborization.
Which is like a tree growing new branches.
Exactly like that. You are physically growing new branches on your neural connections in the executive center of your brain. The brain has to compensate for the restricted path, so it builds new roads.
That makes a lot of sense.
And this completely shatters the old adage that practice makes perfect. Perfect, repetitive practice just deepens existing ruts. Controlled failure struggling against bizarre constraints is the true crucible of mastery. Think about your own life for a second. When was the last time you truly allowed yourself to fail at something entirely new, rather than just retreating to the skills you already possess?
That is a tough question. It is so much easier to stay in our lane. But that ties perfectly into the next major concept, cross-domain learning. Moving beyond just getting really good at one isolated skill, and instead building a versatile cognitive toolkit. The studies highlight the neurodynamic recalibration that happens when you constantly toggle between totally different disciplines.
A great way to visualize this is shifting directly from mathematical reasoning, which lights up the logical parsing networks in the front of your brain, straight over to spatial navigation, which relies on the visuospatial mapping systems in the back of your brain in the parietal lobe.
The research makes a brilliant analogy here. It compares this cognitive toggling to a cross-trained athlete who takes the cardiovascular endurance they build from distance running and repurposes it to enhance their agility in rock climbing. You are taking a problem-solving approach from one domain, like math, and applying it to a completely different challenge.
Right, and it creates interdomain interference, which stops your brain from entrenching those deep monodominant pathways.
Which keeps you mentally agile.
You are building cognitive flexibility. You are teaching the brain how to use its tools in unfamiliar environments.
But it isn't all rigorous math and tonal languages.
Okay.
One of my absolute favorite parts of this deep dive is the focus on unstructured play. We are talking about literal play, like dragging the couch cushions into the living room and building a blanket fort. Why is play without any goals or rules so crucial for the adult brain?
Play fundamentally shifts the operational mode of the brain. When you are doing a goal-oriented task at work, your brain relies on convergent thought. It is desperately seeking the single specific correct answer.
Right.
But unstructured play nurtures exploratory thinking. The internal question shifts from how do I achieve this metric to what can happen if I try this? This mode of thinking actually loosens established synaptic pathways.
So when I'm building that blanket fort, I'm actually doing unconscious hypothesis testing. I'm testing cause and effect, structural integrity, spatial relationships, and even social dynamics if I'm building it with a friend. And because there is no bots evaluating me and no external pressure to get it right, every collapsed fort is just a fun new data point, not a stressful failure.
Furthermore, we cannot ignore the emotional valence of play. When you engage in activities that are intrinsically motivating and playful, your brain releases dopamine. In this context, dopamine acts as a biological save button.
I love that, a biological save button.
It reinforces the very neural circuits you activated during that creative exploration, making the learning process self-sustaining. The data shows that individuals who maintain play-based exploratory environments throughout adulthood show remarkable resilience to cognitive decline later in life. Play is not a frivolous distraction. It is a fundamental mode of neural construction.
I love that idea, but let's be real. As adults, our brains are usually running a million miles an hour, worrying about tomorrow's meetings or paying bills. We have this constant background noise. The research refers to this as the brain's default mode network, or the DMN. How do we turn off that predictive bias and assumption making so we can actually engage in exploratory play or deep learning?
If we connect this to the bigger picture, this is where mindfulness transitions from a wellness buzzword to a structural brain building tool. Structural MRI studies actually show that long-term meditators have increased cortical thickness in the anterior dorsolateral prefrontal cortex.
Which means they have physically bulked up their executive control center.
They have. And that increased thickness correlates directly with a massive 28% improvement in dual task performance. By practicing focused attention meditation, you are downregulating the posterior cingulate cortex.
The posterior cingulate cortex.
That is the hub for all that self-referential, mind-wandering noise and anxiety you mentioned. By quieting that hub, you optimize the engagement of the ventrolateral prefrontal cortex, which shifts your cognition from being entirely reactive to proactive.
You learn to detach from intrusive thoughts, which cuts down on all that mental interference. And that ability to regulate your internal state seems critical for the next strategy they discuss, which is managing strategic uncertainty. When we face something ambiguous, our amygdala naturally flares up and registers it as a threat. How do we fix that?
The process is known as neurocognitive decoupling. Normally, ambiguity triggers a panic response. But through intentional exposure to controlled unpredictability, we can reprogram the amygdala.
Like exposure therapy for uncertainty.
Exactly. The source material uses the examples of improvisational artists and special forces trainees. Their ability to thrive under pressure doesn't come from some innate magical genius. It comes from their repeated exposure to structured chaos. They learn to separate the physiological feeling of stress from the cognitive task at hand.
But there is a clear warning here, too. Unmanaged complexity just causes anxiety and cognitive constriction. You freeze up. The secret sauce is the gradual titration of unpredictability combined with metacognitive awareness. You have to know that you are stressed, acknowledge it, and regulate it.
Yes.
And to really synthesize this kind of mental flexibility, the research points to building critical thinking architecture. You have to become a reasoning engine.
Critical thinking provides the quality control for your cognition. This involves deconstructive argument analysis, taking a complex concept and violently breaking it down into its core premises, inferences, and conclusions to expose the weak joints.
It also involves fallacy detection. Things like cataloging the appeal to ignorance or spotting ad hominem attacks, so your brain develops automatic mental filters. These filters preemptively flag flawed logic in real time. Combine that with Socratic questioning layering iterative inquiries to unearth buried assumptions, and you ensure your independent thought is proactive, not just an emotional reaction to what someone else said.
This raises an important question, though, when we look at this entire framework. How do we reconcile these seemingly contradictory practices? On one hand, we are looking at the surgical precision of deliberate practice, stringent critical thinking, and structured reasoning.
Right.
On the other hand, the findings champion the ecology of randomness found in unstructured play and embracing strategic uncertainty. Even the concept of Bayesian updating, which is the mathematical process of constantly revising your worldview based on new probabilistic evidence, seems heavily structured compared to the broad strokes of building blanket fort.
It does seem like a contradiction at first glance. Strict structure versus total chaos. But the research resolves this beautifully by pointing out that both ends of the spectrum share the exact same objective disrupting cognitive inertia. Structure, deliberate practice, and critical thinking sharpen your mental tools. Chaos, play, and cross-domain learning help you discover entirely new uses for those tools. They aren't opposites, they create a complementary feedback loop.
They form a complete system, and all of these strategies, the sleep hygiene, the language learning, the play, the critical analysis, they are completely futile without habitualization. You have to convert these individual practices into daily neural pathways. Having a growth mindset is not about hanging a motivational poster on your wall. It is a neurochemical imperative. You have to consistently prime your brain for learning.
And you definitely don't have to do it alone. In fact, social networks act as external scaffolds for your brain. Doing collaborative learning, joining a challenging book club, or engaging in a rigorous, respectful debate stimulates dopamine release, which cements those new neural connections. But, and this is a big one, you also have to manage your stress. Chronic stress elevates cortisol levels, and cortisol actively inhibits neurogenesis, specifically in the hippocampus.
The Center for Fluid Intelligence and Memory.
Exactly. If you are constantly stressed out, you are literally halting the birth of new brain cells.
Yeah.
You have to use the mindfulness and relaxation techniques we talked about to stay within your optimal neuroplastic window.
Absolutely.
So what does this all mean? When we zoom out and look at all these different pieces, what is the ultimate takeaway?
The grand synthesis of this material is that cognitive flexibility is not a singular inherited trait. You are not just born smart or not smart. Cognitive flexibility is a multidimensional outcome. It is actively honed through respecting your biological needs, intentionally fracturing your comfortable routines, embracing the messiness of play, and rigorously applying critical thinking.
You are the active architect of your cognitive landscape.
Yes. In an era defined by rapid, relentless technological change, maintaining a fluid intellect is no longer a luxury reserved for academics. It is a fundamental biological necessity for adaptation.
You are a living, rewiring entity, fully capable of designing your own mind. And that brings us to our final provocative thought for you to mull over today. Building on everything we just discussed about the absolute necessity of predictive coding errors, controlled failure, and environmental unpredictability, what happens to our cognitive architecture when we design our modern convenience-obsessed lives to eliminate all physical discomfort? When we automate all of our difficult problem-solving with AI and perfectly curate our digital environments to only show us the opinions we already agree with, does our relentless pursuit of ultimate convenience actually become the greatest existential threat to our cognitive survival? Thank you so much for joining us on this deep dive. Now, get out there and go fracture some cognitive routines today.